Hello and welcome to my video on elastic energy or spring energy. So to start with, Hooke's law tells us that there's a linear relationship between the distance of compression or stretching of a spring and the force that is being exerted by that spring. So if you stretch a spring, maybe this is the regular spring and the distance, and if you compress it so that that all the coils are more compressed. So maybe it's more like this. Well, then the distance that has been compressed is this distance, and that is labeled x in our formula here. And not only is it a distance, it's a displacement, so it actually has a direction. So if you compress it inwards by a certain amount, then the negative here tells us that the force is going to be outwards by a certain amount. Okay. Now, what's also interesting is that work equals change of energy, which we know, and force times distance, which we learned about earlier in this unit. Using Hooke's law with an average force over the course of the spring's compression/stretch, and the above reminder that change in energy is force times distance, we can get the formula for energy. So, basically, because we are talking about the average force over the course of a spring's stretch and compression, well, in the initial equilibrium point, there are no newtons of force being used. But at the end, it's the newtons of force being given by this. So if we're talking about average, we say force 1 plus force 2 over 2. Right? That's an average. That's a regular way of doing an average, except that force 1 is 0 and force 2 is kx. Okay, so this is the F part of FD. So work equals force, that's force part, times by distance, which we can also write as x. So simplifying this, we can actually say, well, the work done by an elastic over the course of its stretch or compression is given by the following formula. S for spring. So kx, and then there's actually double x, so x squared, and then over 2. So that's where that formula comes from. All right, so if we use those two formulas above to solve these next couple questions, the first two are relatively straightforward, and the last one is an experimental thing, which is slightly more complicated. So determine the force required to stretch a spring 10.1 centimeters if the constant is that. So this is relatively simple. We just go force equals negative kx. So it is 0.101 meters times by the k value. I actually kind of did these backwards. I'm going to put it in the right order. 18 newtons per meter over times by 0.101 meters. Okay, and why am I ignoring the negative? Because it doesn't actually tell us what direction we're talking about. The negative is just to remind us, again, like I talked about at the beginning, that the force and the displacement are in opposite directions. That's why the negative is there. All right, so if we multiply those values right now, then we get 1.818 newtons, which we simplify to 1.8 newtons of force. All right, let's take a look at the next one. The spring is stretched too much, will not return to its original shape. This is called a deformed spring. So once you stretch a spring too far, think about it like a slinky. If you bend a slinky, once you've bent the metal, it no longer retains its original shape. So it has exceeded its elastic limit. So that's when it no longer obeys Hooke's law. A spring having a constant of 20.5 newtons per meter is stretched so that it has 0.221 joules of potential energy. Determine the amount that it is stretched, assuming it obeys Hooke's law. If it does not, then it would not be this value, but in which case it would have exceeded the elastic limit. But generally speaking, we can say that the spring constant is kx squared over 2. And what are we looking for? The amount that it has stretched, which is the k value. The x value. So we're going to change this formula around. So it's 2es over k. So multiplying by 2 on both sides. And that gives us x squared. That's not quite done yet. If we square root both sides, that's 2es over k equals x. And so if we now plug that in to our calculator like this, then we get I've forgotten a decimal. There you go, much better. Then we get 0.1468. And this is meters. And so I'm going to change that to 14.7 centimeters. Got 3 sig digs in this question. So that would be our final answer. All right, and here's the more complicated question, since it is kind of a graphing experimental question. So an experiment is used to test Hooke's law, and so one end of the spring is attached to a support, and the other attached to a device for measuring force, a Newton meter. Various forces are shown, so we've got four different forces and 4 different displacements as a result of that. And so I've plotted this with those points there. I'm gonna say probably somewhere around here is a good average. Okay, you shouldn't necessarily have to hit any points, but you're going to get close to some points and further away from others. So you're going to then try to see if there's any points that obviously line up. Almost. But not quite. Okay. So if none of them perfectly line up, then you just kind of pick some spots and go with it. I would pick it on the line. So there is one value. And then there's the other value. We'll get to using those in a second. Let's go ahead and pick another spot somewhere around here. Let's pick this one. So right here. There you go. All right, so in the blue position, I tried to do that right on the point, so we're just going to pretend like I nailed it. 0.225. Over here, we've got 4.3. I'm going to call it just 4.3. It's not perfect, but that's okay. Let's go over to this one. We've got 0.0. 625. Yep. And then over here we've got 1.25. Let's say 1.2. Call it 1.2. All right. So that's important. Oh, I forgot to mention why. Shoot. I should have mentioned why. That's all right. Part B is asking us to determine the spring constant. Well, it's important because the slope we can describe as rise over run. And, well, how do we find the spring constant? Force equals kx. Okay, and we can rearrange that so it kind of fits that same position. So k equals F over x. So rise over run, if it's F over x, then it works. Okay, another way you can see that is if you write y equals mx plus b beside it, you can see that, hey, b doesn't exist, but this m, which is the slope, is the k value. And yes, I know there's a negative, but we're kind of ignoring that for now. So with that all in mind, we can go 0.225 minus, and at the bottom we can have 4.3 minus, and then yellow we can go 1.2, and then up top 0.0625, and then equals, and so now we're just going to plug all of that in, 0.225 minus 0.0625 over 4.3 minus 1.2, and so what we get is 0.0524. Did I do that correctly? Oh, I flipped them around. It should be the other way around. Yeah, I can do this quickly. So this is 0.225 minus, and this is actually 0.0625. And so what we get is 19.07. And this is newtons per meter as our K value, as our spring constant. All right. I hope that this video helped you better understand elastic energy and especially the spring constant. Spring constant is basically kind of like coefficient of friction, where it's just a value that exists in a given situation. It's not a constant of the universe, but it's constant for any given spring. Just like coefficient of friction was constant for any surface. I hope that this video helped you better understand elastic energy, and I hope that you take a look at the next video. Good luck!